So I'm going to talk about perceptions of randomness and some work I've been doing over the last, well, now almost 10 years, actually. So if you've ever taught cognitive psychology, then you will have put up a slide such as this at some point and asked your unsuspecting students which of these two orders is more likely on exactly 6 tosses of an unbiased coin. Heads, heads, tails, heads, tails, heads, or a uniform run of 6 heads. And students want to give the wrong answer, as do you yourself, or certainly if you're me, even though you know that's kind of supposedly the wrong answer. And decades of research have found that people indeed think that these two sequences aren't equally likely to arise from an unbiased coin. Specifically, they seem sort of prone to sort of 3 generalizations that seem wrong vis-a-vis how random processes actually work. First, people think that sequences are more likely if there's some irregularity in order of appearance. So heads, heads, tails, heads, tails, heads seems less regular than a uniform run of heads. They also think that the sequence is more likely if the 2 outcomes, heads and tails, are equally represented in the sequence. And what they perceive to be the sort of random alternation rate, that is how often you switch between heads and tails in the sequence, is inflated relative to chance. And this is typically taken to be evidence of belief in the gambler's fallacy, conveniently abbreviated as GF here and in the following. So people seem to have these biases. Every time I gave these lectures, when I still gave lectures on judgment decision making, I too kind of wanted to say I don't think these somehow feel like they're equally likely, even though I sort of understand what the question is. And the question is how that can really be, this tension can be reconciled. Tversky and Kahneman claimed that it was because people have a sort of fundamental misconception of quite a few features of randomness. In particular, people, according to Kahneman and Tversky, expect that a sequence of events that's generated by a random process will represent the essential characteristics of that process in the long run, even in a short sequence. So this is a particular application of the representative heuristic. So what people have mistaken beliefs about is that things that are true in the long run, they think also has to be true in comparatively short sequences. And another consequence of this same belief is the gambler's fallacy that I've already mentioned. After observing a long run of red on the roulette wheel, for example, most people erroneously believe that black is now due, presumably because the occurrence of black will result in a more representative sequence than the occurrence of an additional red. So people have, on this view, on this explanation, sort of fundamental misconceptions, biases about randomness that are just fundamentally at odds with the statistical properties of the kinds of sequences they're being asked to evaluate. And indeed, there's a sense in which that's actually true, because it is just a mathematical fact that all exact orders of a given length k are equiprobable given exactly k flips of a coin. Right? So all possible orders of 4 heads or tails are equally likely to arise, as are all possible orders of exactly 6 tosses of a coin, which is why the answer to the question posed initially is that they're both equiprobable. But this is not true. Exact orders of length k are not equiprobable as substrings of a longer global sequence. So they're equally probable if you just flip the coin 6 times, but not if you're actually watching a longer temporally unfolding sequence of coin flips, something like this. So that's you're watching this sequence unfold as the person keeps flipping this coin, and you have a finite attention, finite memory, which means that you can probably only remember back so many coin flips, say maybe 4 or 6 or 8, something like that. And if that's the way you experience things, if that's how we're thinking about the occurrence of sequences, then particular sequences of length 4, what happens, what sequences you see in that sliding window are no longer equally likely to occur. In fact, you have to wait, on average, 30 tosses of a coin before you get 4 heads in a row. And you have to wait on average only 16 tosses of a coin before you see 3 heads followed by tails. And that too is just a mathematical fact. So why is that? It's easy to see if you look at the sort of combinatorial tree of possible sequences. So this is the combinatorial tree of all possible sequences of length 4, all 16 of them. And you can see that each branch in this tree is just one of these sequences of length 4. And of course, if you're flipping a coin exactly 4 times, you're just randomly selecting one of these branches of this tree. But what happens now if you think not about sequences of length 4, but sequences of length 3? And you consider sequences of length 3 as subsequences that you see in your little sliding window as you move through a longer global sequence, in this case of length 4. I just couldn't draw a bigger combinatorial tree and still have you be able to read what you see there. So we're interested now is in the occurrence of these 2 sequences, 3 heads or 2 heads and 1 tails, as subsequences in an unfolding global stream that happens to be length 4. Now, the first thing to notice is that there are 4 instances across this combinatorial tree of both of these, right? So on some level, they're exactly the same. And if we flip a coin many, many, many times, we'll see them equally often, reflecting the fact that there are 4 occurrences of each of these. But what's not the same is the way that these sequences are distributed across this tree. Specifically, 2 of the occurrences of 3 heads live in the same branch as subsequences of a longer global sequence of 4 heads. And that's relevant because we just said that flipping a coin 4 times is just randomly selecting one of these branches. Now, if heads, heads, tails is embedded in 4 different branches, then you have a 4 in 16 chance of picking a branch that has heads, heads, tails in it. But heads, heads, heads lives in only 3 of those branches. So you only have a 3 in 16 chance of encountering heads, heads, heads. And these distributional properties are consequential in that they make it the case that as long as the global sequence is finite, local substrings are not equally likely to occur. So this is what gives rise ultimately to these wait time differences. This graph is probably a little bit teeny-weeny. Is there anything you can read at the back about it at all? So running along the bottom, you have all 16 possible sequences of heads and tails, with the perfect runs, just tails or just heads at the edges. And on the y-axis is the expected wait time. And what you see is that there's variability across the wait times for these sequences. The most extreme wait times are for 4 heads and for 4 tails, the uniform runs. This is symmetric because it doesn't really matter whether you label the thing as heads or tails, so it's always going to be the same on either half. And the other sequence that stands out is tails, heads, tails, heads, and heads, tails, heads, tails. So the perfect alternation. So uniform runs and perfect alternations, that is the sequences that appear intuitively as most regular, are in fact also the sequences you're going to have to wait for longest. And that distributional property also means that if you're only observing a random source, such as a sequence of coin tosses, for a moderately long period of time, which seems fair enough because most of us don't sit there for hours on end looking at coins being tossed, those differences in wait time, those distributional differences, translate into what we've called the occurrence probability, which that is the probability that the sequence, the global sequence you see unfolding, will contain any instance of that particular subsequence. And that occurrence plot just follows exactly this wait time graph. So what's emerging here is that over different sequences of length 4, as you increase, as you modify the length of the global sequence, you start to get these emergent differences between the two most regular sequences, perfect runs and perfect alternations. And they seem particularly marked somewhere around in this region, which you might think corresponds to a sort of reasonable amount of exposure to a single sort of random source. In the limit, when that sequence gets longer and longer, that global sequence, you eventually will encounter that branch, and you'll see a whole bunch of heads, probably in an even longer run of heads. But certainly here, there are differences in the probabilities of these sequences occurring at least once in the global sequence you're observing. And at, say, length 15 and even at length 20, the most likely outcome is still that there's not actually going to be a run of length 4 in that sequence at all. Right? Those probabilities are above 0.5. And this is nothing about subsequences of length 4. This is equally true if you were to look at subsequences of length 6. So the basic mathematics of these things are the same. So it was a bit boomy. So this has been characterized in terms of the probability that you will see at least one of these sequences in your global sequence of a given length. But you can also characterize this simply in frequency terms, the account of how often you will see sequences. These are now simulations over many runs of global sequence length 20. And on the left is the distribution, the histogram you get for 4 heads. And on the right is the distribution you get for heads, heads, tails. And you can clearly see that they're different and that the most likely outcome, the most frequent outcome is having 1 heads, 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 tails in the sequence. And the most likely outcome is having 0 of these in a sequence of length 20. And this is just a different way with these box plots of showing that. This is both the mode and the median outcome for length 20. So what does this, as kind of a sort of fun fact, but what does that tell us, if anything? Well, the account we wanted to put forward in 2009 was that, in fact, these biases, when you revisit them in light of this experiential model, don't seem really as much as biases, but rather like actually quite apt descriptions of the actual experience that you have if you're looking at sequences of moderate length with this attentional sliding window, right? So people think sequences are more likely if there's some irregularity in order of appearance. Well, uniform runs and perfect alternations are indeed less likely to be encountered if that's how you're experiencing things. People believe that 2 outcomes are equally represented. Well, there are many, many subsequences if you're looking at sequences length 6. For example, there's 64 different ones. Most of them aren't all that distinct, right? So you might not have any particular reason to notice that they're special. And on that aggregate level, it's certainly true that there are many more of them that have equal proportions than there are ones that don't over the whole set of sequences in that combinatorial tree. And other people had noticed that in the past. And finally, and this is something else that people had noticed in the past, in particular Yakov Kareev, is that even the alternation rate is inflated if your experience is based on comparatively short global sequences. If you're looking at sequences of a length up to only about 20, the alternation rate that you're seeing lies above the long-run alternation rate of 0.5, precisely because you're not seeing that right-hand branch that's just uniform runs of heads, right? That's the thing that's bringing down the alternation rate. So the fact that people assign an alteration rate that's higher than 0.5 is actually in accordance with that environmental experience. So it seems odd from that perspective to call these things biases, because in some way they seem like a fair enough description of what people are actually seeing. So on this account or putative explanation, there's 2 things that matter with respect to experience. One is how people experience random sequences, the fact that they have this they temporally unfold and they have this sort of sliding attentional or memory window. And the second is the fact that it matters how much experience they have. As I've already said, as you make the global sequence longer and longer and longer, right, these asymmetries go away. So this is just one more time in this figure. If you look at the comparison between foreheads and heads, tails, at the top you've got length 20, the middle length 50, and at the bottom you've got length 200. And at this point, these distributions are entirely symmetrical, and they have sort of equivalent mean numbers of occurrence. So that's kind of nice in theory. I thought it was kind of a neat mathematical fact. But of course, with respect to seeing whether this has any real traction in explaining human behavior, you wouldn't want like some kind of experimental test. And the obvious thing to utilize for an experimental test is a manipulation of this global sequence length that people are seeing, because global sequence length matters only on this account. It's completely irrelevant on any other account of randomness perception in the literature. So if your explanation of why people have these biases is the representativeness heuristic, that is a story about the particular short sequence, the local sequence you're being asked to judge. It's irrelevant if you've been tracking that in sequences of length 10 or 20 or 100. It's also irrelevant if you have an account that's based on, in spirit, on algorithmic complexity theory, where you think randomness is a property not of the generating process, but of the sequence itself, like its compressibility. Falk and Konold have an account like that, where they use the memorability, which is supposed to be related to the ease of compression of a sequence, as a proxy for randomness. So things that are easy to remember, things that have sort of compressive short codes, such as uniform run or perfect alternation, they're easy to remember. They're not perceived to be random. Things that are really irregular are hard to remember because there's hard to find short descriptions of those. And that's their account of randomness. But again, it's totally irrelevant. It's property of this local sequence that you're asking about, nothing about how you've experienced it otherwise. And it's also irrelevant with respect to the gambler's fallacy, with respect to accounts such as that by Aiton et al. That think that people who subscribe to the gambler's fallacy, and that's supposed to be most people, are simply confused by the difference between sampling with and without replacement. So the basis for a simple experimental test, if you want to kind of leverage this global sequence length thing and the fact that experience matters in that sense, is to simply give participants in an experimental paradigm the same amount of global experience, but split that, or total experience, but split that into global sequences of different length, which they will wander through with whatever local attentional memory or attentional window they have. And we're then looking for an impact on people's generation and perception or judgment of randomness of how these sequences have been chunked. So specifically, what happened in the experiment was that everybody saw the same 2 times 100-bit sequences of ones and zeros overall, so 200 bits. But in one condition, that was split into 2 global sequences of length 100. In the next condition, it was split into 20 sequences of length 10. And in the final condition, it was split into 40 sequences of length 5. And in the experimental paradigm, all you did was that there was a pre-experiment generation phase where you generated 2 sequences of length 100 that were supposed to be random. Then you merely passively observed these sequences in whatever condition you were in, and then you regenerated, another sequence, another 200 bits, again in 2 sequences of length 100. And the question is, does this chunking manipulation make any difference? And I probably wouldn't be standing here if it didn't, telling you about it, and it clearly does. So what's on the y-axis here is the alternation rate. And on the x-axis are the 3 different conditions, and the dark bars are the pre-exposure, the white bars are the post-exposure. So the thing to notice with respect to the pre-exposure, first of all, is that the average alternation rate in the sequences that people generated is at about 0.6, which replicates many, many other studies in the literature. So it's an inflated alternation rate relative to the long-run average, which is 0.5. And that comes down by just passively watching these 200 bits. But the extent to which it comes down is really influenced by condition. So changing the length of this global sequence has an effect in that it comes down basically to the long-run average in the first condition, slightly above in the 20 times 10 condition, and very little changes in the 40 times 5 condition. So a different way of seeing that is I can show you the actual histograms that people generate. These are as a plot of the different frequencies with which different alternation rates are produced in the sequences that people generate. This is pre-exposure across the 3 conditions, and this is the post-exposure. And you can see that in these 2 conditions, the whole distribution shifts so that its mean is now centered broadly around the long-run average. A second way of looking at that same data is to think about local subsequences now and think about 4 heads versus heads, 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 tails, just as I used in my initial example. And we can plot that ratio, which is what we've done here on the y-axis. And again, we have the pre and the post exposure. In the long-run sequence, the ratio between those 2 is 1 because the overall, there's equal numbers of those in the combinatorial tree. And in the long-run average, that ratio becomes the same. And we see that in all conditions, it rises as a result of the exposure, but it does so again as a function of condition. And finally, we also asked people to judge random sequences, which we took from the Falcon-Konald Psych Review paper, where there were sequences, 10 sequences that people had to judge the randomness of. And there too, we see an effect of condition that broadly mirrors the other 2. The actual data from which those plots are generated is this. For each of these sequences, we plot the proportion at which they're judged to be the most random sequence and find the best fitting function for those, and then compare that across pre and post exposure. So that's the experimental data. It shows a clear effect of this chunking manipulation, of manipulating the global sequence length, even though on some level of description, the exposure is exactly the same across all conditions. It's really just different in how it's chopped up. But we did one more thing with respect to the gambler's fallacy in this paper, is that we actually also asked people about their beliefs. So all of our participants pre-exposure and some of our participants even post-exposure show these inflated alternation rates, which in the literature have been taken to be evidence of belief in the gambler's fallacy, because it's been taken as an indication of the fact that people think they have to switch from heads to tails more often than they should because they think these long runs are improbable, and as you build up a run, you start to think it becomes more likely that it's now going to flip. But when you ask people, at least the people we ran this study with, which outcome is most likely following 5 heads, is it heads, another heads, tails, or they're both equally likely, only a minority actually explicitly endorse the gambler's fallacy and say that switching is more likely in this case. The majority correctly say it's equally likely. And furthermore, when you split these people and look at the alternation rates that they produce, they're not really different. So there's a dissociation between the alternation rate that people generate in this task and their explicit belief in the gambler's fallacy. And in fact, if you take the alternation rates and the distributions of alternation rates, here are the marked symbols are all the people who explicitly believe in the gambler's fallacy, and they've been positioned within the distribution that's estimated on the basis of the data of everybody else, with the blue bits signaling the 95 the 5th percentile, and they're really not different, right? Those two triangles might be a bit different. But most of these people don't really look different, and that suggests rather strongly that alternation rate just isn't an appropriate empirical test of belief in the gambler's fallacy. Because the same people who are producing in our pre-test exactly those inflated alternation rates that you see everywhere else in the literature and that have been taken as evidence of a belief in the gambler's fallacy are explicitly telling us that they don't believe in the gambler's fallacy. And not only are they telling us that they don't believe it, but there is actually an explanation in the account here and in the change that happens as a function of the manipulation of why they produce the alternation rates that they do. So as an interim conclusion, experience, as defined by a sliding window account, moderates randomness perception. Further experience shifts behavior to the true characteristics of the process, of a truly random process, even a very limited amount of further experience, just passively watching 200 tosses of a coin effectively. And over-alternation just isn't a suitable measure of belief in the gambler's fallacy. And these results, as I've said before, they're not predicted by any other account of randomness in the literature, whether it's representativeness, entropy, ease of encoding, or confusion about sampling with replacement. And to just pause for a second on this issue of sampling with and without replacement, it's also interesting, at least to me, that if you contrast a process of sampling with replacement and a process of sampling without replacement on this environmental model, and look at what the resulting graphs look like, graphs of the kind that I showed you initially, they're virtually indistinguishable. You can't really tell apart, just on the basis of that experience, if you buy into this experiential model, whether you're in a context of sampling with or without replacement. So on the left-hand side is just a global sequence of length 20 with replacement, which is what you saw before as one of the values in those colored plots, right? But these are now these sequences of length 4 drawn from, and a global sequence of length 20 drawn from an urn with 2,000 balls, half of them red and half of them blue, 200 balls, 50, 30, and even just 20. Right? So in everything but here, the gambler's fallacy is not a fallacy. But it's really hard, looking at those graphs, to say that they look in any way radically different. Which to me seems a pretty good argument for saying that purely experientially, you don't really have a hope in hell of observing the difference between sampling with or without replacement. So it wouldn't actually be surprising if people were confused about it, right? What you need is some kind of conceptual knowledge, some kind of meta-theory about this. And that meta-theory might seem simple to us at this point in time, but it really is anything but. And there's two ways that I want to illustrate this. One is that you can come up with contexts that sound extremely similar to the gambler's fallacy, which aren't fallacious, right? So this betting game, for example, which we also proposed in that 2009 Psych Review paper, is if a prior limit of 20 coin tosses were decided, and one were to bet that substring HHHT would occur as opposed to HHHH, right? I pick HHHT, you pick 4 heads because you think they're the same anyway, then who would win on average? Now, before hearing this talk, you would have thought, well, they're going to be equally good, and to believe otherwise is just to believe in the gambler's fallacy, and this sounds an awful lot like the gambler's fallacy. But of course, one of these is a winning strategy, right? If we implement that as a game where you get $1 each time heads, 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 heads occurs, and you lose 1 each time heads, 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 tails occurs, and nothing happens if both of them or neither of them occur, then I will very rapidly win this game. Because the expected value, the probability of you observing your sequence is 0.48, and the probability of me observing mine is 0.75. Yet superficially, that seems really similar in many ways. And in fact, this is kind of so counterintuitive that the only reason I plotted that game and published it in this 2010 reply is because we actually got a reply to our psych review paper by people who said this isn't true. But it is. So while it's true that the gambler's fallacy is a fallacy, right? You need a well-developed meta-theory, probability theory, to understand that it is. You need a body of conceptual knowledge. And that body of conceptual knowledge itself is non-trivial. It's a fairly late addition to mathematics. If you sort of look at the overall history of mathematics, it's certainly not something that's been around for thousands and thousands of years. So it seems rather odd to label people as irrational for having mistaken beliefs about it, even where they do. Right? We don't normally think of people as irrational just because they don't know something that they can only know by being told it. Right? You might think they're ignorant or poorly educated or something, but you wouldn't think of them as irrational. That seems to me to be exactly what's going on in this context. So one more thing on the experimental data, because the question raised here that you might be wondering about is, what is it that participants are actually learning? They're clearly learning something in the chunking experiment that I showed you, but what is it that they're learning? And we've probed this in a further study more recently, which involves people, again, observing a whole sequence of digits. In this case, 600 digits over 30 blocks of length 20 with a distractor task in between. And after that, they have a generation task where they do the same thing. And in this study, this is one of the first things we did. We actually ran this before the other study. It just got published later. We wanted to make really sure that people paid attention to these sequences. It's actually much more experienced than the other study. But so we also gave them a tone that varied. There was a high tone and a low tone, and the ones went with the high tone, and the zeros went with the tone. And then when we tried to publish that, people said, oh yeah, but you just have this tone. How interesting is that? So we then also ran another study that has a condition but without the tone. And this is what you get. This is what you would expect. These lines are what you would expect as the long run frequency if you did this many, many, many times for sequences of length 20 and counted the positive occurrence of each of these different sequences. These are, again, our familiar sequences of length 4 running along the bottom here. And what you see at the top is the pre-generation phase. The dots are now the average frequency generated by participants. Pre-silent condition, then the post-silent condition, and then third from the top, the pre-data from the tones, and then the post-data from the tones. And people get closer to the true frequencies of the theoretically random process. But people's data actually look a lot better when you compare it to this, which is just these occurrence probabilities. Again, the probability of occurrence for these different sequences that I started out by showing you. And here, certainly after the experience, so in rows 2 and 4, except for the perfect uniform runs, where people are still not extreme enough, they kind of lie on or within the confidence intervals of what the true characteristics of a random process should be like. So how do they get there? Well, one thing you might say, well, is it just mimicry? You showed them all of these things. Maybe they're just imitating that, right? And that might not be very interesting. But across the bottom are these occurrence probability graphs, and across the top are the actual occurrence probabilities that people saw in the sequences that they observed, because they all saw the same sequences. And what they've moved toward is what you would expect from a random process, not specifically what they saw in that sequence that they were observing. So how did they get there? So I'm just going to gloss over this in the interest of time. These data can be modeled on the simple assumption that you just assume this experiential sliding window model, and that the behavior and the shift in behavior is largely driven by the sensitivity to differences with respect to long runs and the other sequences. So in this model, you start by randomly picking an item, and then you generate another item, and then you generate another item. And at relevant points, you look, when you come to think about your next item, at the other sequences of length 4 and their occurrences in order to sort of inform your decision about whether you're going to produce another one of these, another 1 or another 0. And you can tweak, basically, in the model. You can boost or deboost the probability of one outcome to bring things into alignment with these sequences. So you can effectively tweak the rate at which certain local subsequences occur. And it turns out that if you do a bunch of simulation and model fitting, that you can find a rate for this simple single boost parameter that brings the data quite closely into alignment with the participant data. And what happens in the model is that you're basically boosting just these two figures, 001 and 1110. So what you're learning effectively on this model is to produce slightly longer runs than you previously would have. And if that's basically the only thing you're going to tweak, then you already become much, much closer to the true characteristics of a random process, and you get reasonable fits of the human data. So, final conclusions. We're sort of in the wrap-up phase. How random generated sequences are depends on what features you're looking at, right? With this last set of data, when you just compared them with the frequencies, the long-run frequencies, people looked kind of all over their shop, and there was sort of systematicity that didn't really make sense. But that systematicity did seem to make sense when you considered occurrence probabilities. There's a simple generative model that incorporates this sliding window and sensitivity to runs that provides reasonable fits of the data. And this in and of itself, this work, I think of as just one example of a wider literature that I also wrote a paper on at some point that has emphasized that there's actually quite a few different contexts in the judgment and decision-making literature where seeming irrationalities can be explained by the fact that the samples that people are considering, or the samples that people have experienced, are comparatively small and the statistics of those samples simply don't match the long-run statistics. So that if we pay closer attention to what people are actually experiencing, these deviations between experience, the true characteristics of a variety of processes and people's perceptions of them is brought into closer alignment. So in conclusion, I've introduced you to this experiential account, which involves this simple idea that we view temporally unfolding sequences through some kind of sliding window, and what our experience is building up over is what appears in that sliding window. That's what we're sort of sensitive to. And that's where our frequencies and probabilities come from. Further experience, very limited further experience, shifts behavior to the true characteristics of a random process. And as a side effect of showing that, we've shown also that over-alternation just isn't a suitable measure of belief in the gambler's fallacy. So I think with that, actually also much of the evidence empirically that people supposedly believe in the gambler's fallacy actually collapses. If you no longer buy the idea that over-alternation per se is an indicator of belief in the gambler's fallacy, much of that evidence is gone. And we showed you these chunking effects which manipulate global sequence length by keeping overall experience context constant that are inexplicable on any other account. What's also important to me is that the point I've already made in passing, is that it seems odd to label as irrational a perception that actually fits with experience, and that one could overcome only by being told the answer. Right? On some level of description, these biases seem like sort of fair enough descriptions of what you actually see and experience. And at the same time, as I showed you with the comparison between sampling with and without replacement, you can't really learn that difference just from watching stuff unfold. You couldn't tell whether a particular source was with or without replacement on this experiential model. Right? You need some kind of some kind of reasoning, some kind of modeling, some kind of meta theory to get to that answer. And this is important to me because this means that the experiential account actually reduces the tension between something that I thought was really, really puzzling to me before, and was actually one of my motivations for thinking about this stuff. Because it always seemed really implausible to me that people would be terrible at perceiving randomness and sort of imposing structure where there is none. Given that, if anything, when I look at the world and the inductive judgments people make about the world, I see incredible success. Right? At any point in our life, there's like zillions of pairwise contingencies and things going on. And we seem really good in picking out things that genuinely reflect some kind of structure. And that seems the thing that we don't understand how we do that, and the thing we want to have an account of. And that amazing capability seems even more deeply baffling if you think we just sort of randomly impose structure where there is none. And that tension sort of starts to collapse on this account. And finally, it's really important in the context of this explanation, but I think in wider judgment decision-making context, that human experience isn't just finite, but often extremely limited. And that small samples are systematically different from large samples. Ralph could tell you a lot about that in other contexts. And that if we want to understand behavior and evaluate the rationality of behavior, then those differences need to be taken into account. Thank you very much for your attention.